So this is E619, lecture 7. So we started with an inverter with a resistive load, then went to an inverter with an NMOS load, and finally we are now at a CMOS inverter. And we quickly saw that the VTC for the CMOS inverter, V0 versus Vin, has the following shape, where VOH was equal to VDD and VOL was equal to 0 volt. Now, we are now going to look at the same plot using a load line plot. Were you able to do this? Were you able to derive it? Let's quickly go through it. So you have an inverter like this. So what we'll do now is we are going to plot the I0 versus V0 for both the PMOS as well as the NMOS. So let's start with the NMOS. We want to do I0 versus V0. Now quickly tell me, for the NMOS, what is I0? This is same as the drain to source current for the NMOS, right? And what is V0? It is the VDS. So you're basically looking at the ID versus VDS plot for the NMOS. Now we'll do this for multiple voltages. Let's say 0, V in 1, V in 2, V in 3, and finally VDD. And of course, the relationship between them is as follows. This we should be able to do very quickly. For 0, the current is 0. V in 1, the current will look like this. V in 2, V in 3, and finally VDD. Okay, so now let us get the same plot for the PMOS. What is I0 for PMOS now? This is the current from source to drain. What about V0? This is equal to VDD minus VSD. Okay, so I will start by first plotting ISD versus VSD for different values of Vn, and then we will shift it such that I can get ISD versus V0. So we are looking at ISD versus VSD for the same Vn values as shown here. So when Vn is equal to 0, what is the VSG for the PMOS? VSG will be equal to VDD. So how would the curve look like? This is the maximum source to gate voltage that you can have, right? So for Vn equal to 0, you will have a curve like this, the highest curve. Now for Vn1, the curve is going to be lesser than this. Then you will have the blue curve, the green curve, and finally when Vn is equal to VDD, what is the VSG? Equal to 0, right? So you will have a flat line here. So now if I want to plot ISD versus V0, how should I change this? So ISD, which is same as I0 versus V0. Right. So basically when V0 is equal to VDD, what is the value of VSD? When V0 is equal to VDD, should mean that VSD is equal to 0, right? So for all points close to VDD, I'm looking at these points. And when V0 is equal to 0, I'm dealing with VSD equal to VDD. Okay, so I'm going to transform all these curves into this plot. So my red curve is going to look like this. V in 1, V in 2, V in 3, and finally VDD. So now I have to put both these in the same plot and find out where these lines are intersecting. Is this clear? So let me copy this. Right. So this was our VDD. Now I'm going to draw the curves corresponding to PMOS on this. So this is for V in equal to 0. Okay. So we had 0, V in 1, V in 2, V in 3, and finally VDD. So corresponding to V in equal to 0, where is the intersection point? Here. This is where this red line and the red line for the PMOS, red line for the NMOS is intersecting. Right? Similarly, for V in 1, the intersection point is here. Both the blue curves are intersecting here. The green curves are intersecting here. And finally, the violet curves are intersecting here. Okay. So quickly looking at this, can you tell me what is I naught when V in equal to VDD? So when V in is equal to VDD, corresponding to the violet curve, the intersection corresponds to I naught equal to 0. So I naught is equal to 0. Again, what is I naught when V in equal to 0? The red intersection point, which is 0. So when is I naught getting the maximum value? Roughly, in this plot, it has come out to be at VDD by 2. But what comment can you make about the region of operation of NMOS and PMOS? Both are in saturation region here, right? The curves are flat when they are intersecting. So here, both NMOS and PMOS are in saturation. Now, whether it is velocity saturation or pinch of saturation will depend on the relative values of VGS minus VTN and the VD sat values. Okay, now from this, can you derive the V naught versus V in plot? So please do. All right, when Vn is equal to 0, what is the value of V naught? Vn equal to 0, corresponding to the red curve, right? We have put both the red curves are intersecting at this point, corresponding to V naught equal to VDD. So Vn equal to 0 gives you this point. Vn equal to Vn 1, the value is lesser than VDD, but still looks much greater than VDD by 2. So we are somewhere here. Vn equal to roughly VDD by 2. You are sort of in the middle of the range. So here, then you have V in 3. That gives you a value here. And finally, when Vn is equal to VDD, what is the value of V naught? What is this value of V naught? 0. So you have the point here. Now, if you had drawn with sufficient values of Vns, you would have been able to connect this properly into a curve. Is this clear? Any questions on this? Okay, good. So now let us move on to a few points regarding the switching threshold of the inverter. What is another name for this? Midpoint voltage. This is also called as the trip point of an inverter. And like I mentioned, we usually represent using the variable Vm. So quickly tell me, how would the ideal VTC curve look like? So we need very less gain in the regions of stable logic high and logic low. So very less ideal condition, we would like it to be 0. And we need very high gain during the transition region. Again, very high. Ideally, we would like it to be infinity, right? So this is the ideal VTC curve. And usually we place this transition around VDD by 2. Now, if I pass a line, V0 equal to Vn, then the point where this intersects is called as a trip point or the midpoint voltage of this inverter. So this point is basically Vm, Vn. And what is the ideal trip point? This will be equal to VDD by 2. Okay. So now that we have revised what the ideal trip point is, let us do the calculation for the inverter. Right? So we are going to calculate the switching threshold for an inverter, and we'll do the calculation in 2 parts. We will first assume that the inverter consists of short channel transistor, and then we'll do the calculation and see what we can understand from the equations that we derive. And following this, we'll repeat the calculation for an inverter consisting of long channel transistors. So let us calculate Vm for a short channel inverter. So let's start with the assumptions we are going to make. So first, to keep the calculations a little simpler, we are going to assume that the channel length modulation is 0. It is possible to do the calculation with a finite value of lambda n and lambda p. What will happen is you will have a quadratic equation and the calculations will be cumbersome, and you'll finally get a result which is sort of like a mathematical exercise, right? You will not be able to get much insight based on that equation. So again, our idea is not to turn this into a mathematical course, but to get a feel for the way how we have to change the W and L for a transistor, right? So with this in mind, we will start with the assumption lambda n equal to mod lambda p equal to 0. Next, can you tell me what the region of operation of the NMOS would be? Which saturation? Velocity saturation, right? So we have to look at the minimum value of 3 quantities: VGS minus VTN, VDS, and VD Saturn. What is VGS minus VTN? It's the midpoint voltage. So this point is Vm. This is also Vm, right? So this is Vm minus VTN. VDS is Vm. And of course, VD Saturn is whatever value corresponding to that device. Now, of these, can it ever be in linear region? It can never be in linear region, right? Because you have Vm and Vm minus VTN. So either you will get this as the minimum value, or you will have VD Saturn as the minimum value. Since we are assuming that this derivation is being done for short channel inverter, we will assume that VD Saturn is the smallest value. So NMOS is now in velocity saturation. Let's repeat the same exercise for the PMOS. Again, we have to look at 3 quantities: VSG minus mod VTP, VSD, and finally mod VD sat P. So what is VSG minus mod VTP? So VSG is VDD minus VM minus mod VTP. VSD, right, this is VDD minus VM. So again, of the three values, the minimum value could be either VD sat P or VSG minus mod VTP. We are starting with a short channel inverter. So we will assume that VD sat P is the minimum value, and therefore PMOS is also in velocity saturation. So now all that you have to do is equate the currents under these conditions when the input and output is VM, and then derive an expression for VM. So please do. The current through the NMOS is mu n COX, VD sat n, VSD minus VTN minus VD sat n by 2. This will be equal to UPCOX mod VD sat P into VDD minus VM. So this is VSG minus mod VTP minus VD sat P by 2. So I'm going to take this factor. Oh, wait, there is a W by L missing, right? So I'll write the W by L with the subscripts to differentiate between the NMOS and the PMOS. Now I'm going to take this factor to the RHS. And I'll call this whole thing as R. Now can you give me the expression for VM? So you should have gotten the expression VTN plus VD sat n by 2 plus R into VDD minus mod VTP minus mod VT sat P by 2. Is that all? Divided by 1 plus R. So this is still a very complicated looking expression. So we are going to do further simplifications to understand this. So the first assumption we are going to make is to assume that the length of both the transistors, LP and LN, will be equal to the minimum length, right? Which means the expression for R is now a little simplified. What is the expression? This is mu P COX by mu n COX into mod VD sat P by VD sat n into WP by WN, where the initial portions are the technology parameters and WP by WN is the parameter under your control. Now next we are going to assume that the properties of the NMOS and PMOS are symmetric, meaning VTN is equal to mod VTP and VD sat n equal to mod VD sat. We will also assume that the supply voltage is much, much greater than VTN plus VD sat n by 2. So can you simplify the equation based on these assumptions? Retain R as it is in the expression, but tell me what is the value of Vm? So you have a VTN here. We just said that mod VTP is equal to VTN. So you can replace this with VTN and bring it out. So it will be VTN into 1 minus R. Similarly, VD sat n by 2 into 1 minus R, right? So this becomes R times VDD plus VTN plus VD sat n by 2 into 1 minus R divided by 1 plus R. So now we are going to analyze this for 3 conditions. When R is equal to 1, now this corresponds to WP by WN being equal to mu n COX VD sat n divided by mu P COX VD sat P. We have not considered it to be equal. You can cancel it, right? I'm retaining the equation as it is. So if I assume R is equal to 1, what is the value of Vm? Everyone is getting VDD by 2. So this gives you VDD by 2. Now, if R is much, much greater than 1, that means WP is much, much greater than WN. So how much greater? It should be greater, much, much greater than this factor, right? In this condition, what can you say about Vm? Can you look at the equation and tell me? So R is much, much greater than 1. So from the denominator, you can have only R. 1 plus R, you can approximate it to be R. 1 minus R, you can approximate it to be minus R. So then this becomes VDD plus VTN plus VD sat n by 2. And then we mentioned a condition here that VDD is much, much greater than the other factors. So it will become closer to VDD. So this goes closer to VDD. Now, if R is much, much lesser than 1, can you tell me what comments you can make about Vm? Do you get 0 from here? If R is much, much greater than 1, what would be the denominator? Sorry, much, much lesser than 1. Denominator is 1. You have R here, and this is also 1. So now it depends on the relative magnitudes of R and how greater VDD is more than this, right? But you can definitely say that this will be a small value. Is that clear? The smallest it can go is VTN plus VD sat n by 2 from this equation. But it depends on how much larger R is compared to 1 and how much larger VDD is compared to this factor. Okay? So you can say that Vm is a small value, which is definitely smaller than VDD by 2. Is this okay? So all that we have said now is that if you started with an ideal VTC curve like this, let's say you designed for VDD by 2, and to get this, you have to design for R equal to 1. If you make your R larger, the curve is going to shift to the right side. If you make your R smaller, the curve is going to shift to the left side. Is this okay? So in this direction, WP by WN is increasing. And in this direction, WP by WN is decreasing. So now another question to you. If I tell you that the value of R is close to 1, it's either slightly lesser than 1 or slightly greater than 1. Then how can you simplify this equation? You can ignore 1 minus R and 1 plus R, right? So then this becomes R VDD divided by 1 plus R. So in the denominator, we already said that this factor is much smaller than VDD and 1 minus R is close to 1. Sorry? 1 minus R is close to 0. 1 minus R is close to 0. So this is also a small number. This is also a relatively small number compared to VDD. So we can ignore this factor altogether. So we have seen the equation. Now let us see if we can get an intuitive explanation for this. Is the derivation okay for you? Okay. Now let's see if we can get an intuitive explanation. So I'm going to exaggerate the transition region. Let's say I have set my WP and WN such that VDD by 2 is the midpoint voltage. So if I apply VDD by 2 at the input, I get VDD by 2 at the output. So what that means is, if I were to plot the V0 equal to V in line, it is going to intersect at VDD by 2. Okay. Now let's say, keeping all the other conditions as it is, I increase my WP. What happens to the current through the PMOS? It increases, right? What happens to the current through the NMOS? It remains the same, right? So now can you tell me, how should V0 change such that the current through the PMOS will reduce and current through the NMOS will increase? V0 should increase, right? Because clearly right now it is not steady state. So V0 has to increase above VDD by 2 so that the current through the PMOS will reduce and current through the NMOS will increase such that it can again achieve steady state. So corresponding to the input VDD by 2, now our output is going to be more than VDD by 2. That means the new curve is going to look like this. So your new midpoint voltage is this, which is to the right of VDD by 2. This is higher than VDD by 2. This is okay. And we can repeat the same exercise with the NMOS transistor. Let's say we double or we increase the width of the NMOS transistor. Now the current through the NMOS has increased. Current through the PMOS is still remaining same. This is not steady state. To achieve steady state, in what direction should we not change? What should happen to the VSD of PMOS and VDS of NMOS? VSD should increase, right? Which means V0 should decrease. So now the new point corresponding to the input VDD by 2 will be lower, which means your curve is going to look like this. Therefore, your midpoint voltage is also lesser. This is clear? So I have given you this explanation, taking into account the channel length modulation also, but we have derived the equations without taking into account the channel length modulation, right? So which means even if I don't consider the channel length modulation, I should be able to come up with an intuitive explanation. So this I leave as a homework to you. Please go back and think about how you can come up with an intuitive explanation to explain the shift in the midpoint voltage, even if you don't consider channel length modulation. Okay. Oh, so let's assume that channel length modulation is 0, right? There is no lambda. Then the current equation is independent of V0. Okay, so what we have figured out now is that we have the potential to change the trip point of an inverter by adjusting the WP and WN. So then the question is there an ideal trip point that we would like to have? So basically, if I take the ideal VTC, it will try to move in the, okay, how? Then the other transistor can move into the linear region. That is a possible explanation. The other way to think about this, then we can discuss it in the next class. Okay, so now initially I started off by saying that we would like the trip point to be VDD by 2. But is there any particular reason to keep it at VDD by 2? I mean, now we have the power to shift it to the left or right. So why not shift it to the left or right? Why keep it at VDD by 2? Why is symmetry important? Sorry? Correct. But is there now that you have learned a lot of terms related to the inverter, noise margin, correct? This is to maximize noise margin for both the high and the low logic levels. For example, let's consider an ideal VTC curve as shown here. Let me call this point as VM. Can you tell me what is VIL and VIH? Both are equal to VM, right? So now what is noise margin high? This will be equal to VDD minus VM. And noise margin low, this is equal to VM, right? So if I choose VM to be equal to VDD by 2, then both the noise margins are equal and they are at their maximum value. I mean, both of them are maximized at the same time, right? But that said, this is not set in stone. And depending on the application, you may choose to have your trip point slightly away from VDD by 2. I can give you an example. Let's say you know that your ground signal is very noisy, right? Which means you might be dealing with square wave like this. So then how would you choose your trip point? Yeah. So your VDD by 2 might not be able to detect the logic 0 correctly. It might get triggered at these points, right? So instead, you would choose to have a trip point which is slightly higher than VDD by 2. So depending on the application, you can design it to be higher or lower as required. So now we have done the calculations for the short channel inverter. We will repeat the same for the long channel inverter, right? We will again start with the assumption lambda n equal to mod lambda p equal to 0. What is the region of operation of NMOS? This will be in pinch off saturation. So again, we have to look at the minimum of 3 quantities. Minimum of VGS minus VTN, which would be VM minus VTN. VDS, which is VM, and VD sat n. Because we are dealing with a long channel transistor, the value of VD sat n is expected to be higher than VM minus VTN. Therefore, the minimum value is expected to be VM minus VTN. Hence, this is in pinch off saturation. What is the region of operation for PMOS? Same, pinch off saturation. You can repeat the calculation, repeat the same process for the PMOS as well. So now we equate the currents. Half mu n COX Wn by Ln into Vm minus Vtn the whole square is equal to, what is this equal to? Half mu p COX Wp by Lp. What is VSG? VDD minus VM minus mod VTP, the whole square. So we'll do quick simplifications. Half and half will get cancelled. I'll take this quantity to the RHS. And we call the whole thing. Instead of calling it as R, to make the calculation easier, I'm going to call it as R square. Okay. So now can you solve and tell me the value for VM? VTN plus R, VDD minus mod VTP divided by 1 plus R. To get VM equal to VDD by 2, what should be the value of R? So we'll make the same assumptions all over again. First step is that Ln equal to Lp equal to Lmin. And we'll assume symmetric characteristics for the PMOS and NMOS. So VTN equal to mod VTP. Now for VM equal to VDD by 2, what is the value of R? 3. R should be equal to 1. And this corresponds to WP by WN equal to mu NCOX by mu PC. So again, you can analyze this. I will leave as a homework to you. You have to analyze it for R much, much greater than 1 and R much, much lesser than 1. The same thing that we did for the short channel plan. So now let's quickly do a numerical problem. So the NMOS characteristics are as follows. VTN is 0.43 volts. VDSAT is 0.63. And mu NCOX is 115 microampere per volt square. For the PMOS, mod VTP is 0.4 volt. VDSAT P is 1 volt. And mu PCOX is 30 microamperes per volt square. It is given that VDD is equal to 2.5 volt. Can you find the ratio of WP by WN for VM equal to VDD by 2? Right. Now what should we do? So we have done calculations for the midpoint voltage. What is remaining? What analysis did we do for the resistively loaded inverter? Power is there. What else? Something related to the VTC we had derived, right? We had looked at the noise margin for the resistively loaded inverter. We calculated VIH, VIL. We already had the VOH and VOL. Then we could do the noise margin analysis. So we'll repeat the same exercise again. So again, we'll first do this for the short channel inverter and then follow it up with the long channel inverter calculations. Okay, so let me remind you what was VIH and VIL. In the V0 versus Vin curve, What is VIL? Where the gain becomes equal to -1. So the points at where the gain equal to -1 we mark on this curve. And this corresponds to, is this VIL or VIH? This is VIL and this is VIH, right? Now we can of course do this calculation. There will be dependence on VDSAT and there will be dependence on lambda, and it will be a very nice mathematical exercise to do. But again, we want to find something quickly for our first cut simulation, right? Our first design. And to do this, we sort of do a linear piecewise approximation. So how we do this is as follows. You first find out the midpoint voltage of this VTC. Let's say this is here. You calculate the slope at this point, at the midpoint voltage. So you calculate the slope at Vn equal to V0 equal to Vm. Let's say the slope is equal to G. Then you draw a line passing through this Vm with the slope G. So now this is a straight line. You also draw a line corresponding to VOH. So another line with slope equal to 0 and another line with slope equal to 0 corresponding to VOL. And then you mark the intersection points. So that will be these two nodes. And we say this is now our VIL and this is our VIH. So when you're doing your designs, this is a quick way to calculate, to estimate your VIL and VIH. And it turns out, so you can see that there will be some small error, but this error is usually lesser than 5%. So this is a very good estimate for you to work with. So if I have VIL and VIH using this method, can you tell me what would be the expression for VIL and what would be the expression for VIH? You can assume the midpoint voltage as Vm and the slope as G. So can you give me an expression in terms of VOH, VOL, which is VDD and 0, and Vm and G? So the idea is, what is the Vn value below which the input voltage is considered as logic 0? How would I find this? Yeah, find the equation for the line, right? You basically calculate the slope in terms of Vm and VIH in one go. And in the next step, calculate the slope in terms of VOH and Vm and VIH. So let me help you with VIH. G can be written as 0 minus Vm divided by VIH minus Vm. Right. So rearrange this. Tell me the expression for VIH. This should be equal to Vm minus Vm by G. So is VIH greater than Vm or lesser than Vm? How? Is G positive or negative? G is negative, right? The slope of this line is going to be negative. Okay, so this G is negative. So minus Vm by G is a positive quantity. And as you expect, VH is going to be greater than Vm. Similarly, can you give me the expression for VIL? Vm plus Vm by G? It should have VDD, yeah. VDD minus Vm by G? Only so much or something else should be there? So the expression should be Vm plus VDD minus Vm by G. So now let's do a quick sanity check. Let's say my G is equal to infinity. Can you tell me what is the value of VIH and VIL? So G equal to infinity, and also assume VM equal to VDD by 2. Both of them you should get as VDD by 2. So with the assumption G equal to infinity and VM equal to VDD by 2, all that I said was we are looking at the ideal VTC curve where the transition region has infinite gain, and this is happening at VDD by 2. So as we saw for the ideal VTC earlier, VIH and VIL will be equal in this case. So now only one question is remaining in this case. We don't know what is the value of G. How do we calculate G? Yeah, equate the currents corresponding to VM and differentiate with respect to VM, right? And substitute the values. So I'll show you how to do the calculation, but I'll not derive the whole thing in the class, right? So G is basically dV0 by dVin corresponding to Vin equal to V0 equal to Vm. So we are assuming short channel transistors, which means what would be the region of operation for both the transistors? It will be in velocity saturation. So let me write the equation. Mu n COX Wn by Ln into Vd sat n, Vn minus Vtn minus Vd sat n by 2. So we are going to keep the value of lambda, 1 plus lambda n into V0. So why we need to put the value of lambda here, I'll tell you once I derive the final expression. So this will be equal to mu p COX WP by LP into mod VD sat P VDD minus Vn minus mod VTP minus mod VD sat P by 2 into 1 plus lambda P into VDD minus V0. So you can do the differentiation. So you differentiate it with respect to Vn, find out dV0 by dVn, and then you can make the appropriate substitutions. For example, dV0 by dVn is now your G, right? V0 will be equal to Vm, Vn will also be equal to Vm. And you will get the result as follows. ID as a function of Vm. So whatever is the drain current at Vm into mu n COX W by L of the NMOS transistor into Vd sat n minus mu p COX W by L of the PMOS transistor into Vd sat p divided by lambda n plus mod lambda p. Right? So the value of lambda n and mod lambda p is expected to be small. Therefore, you will get a relatively large G here. Now, the reason why I did not neglect the value, can you guess why we did not neglect the value? Right. If lambda n and lambda p were equal to 0, your G will be equal to infinity. And if G is equal to infinity, you are basically looking at the ideal VTC characteristics. Right. So for this particular calculation, I mean, you can start out assuming lambda n and lambda p equal to 0, then you'll get stuck. And then you'll realize, okay, lambda n cannot be 0, and then substitute and derive. So now what should we do? Noise margin for a short channel inverter is done. So we should at least make some comments about the noise margin for the long channel inverter, right? So let us quickly look at that. So here, when we are concerned with a long channel inverter, we know that it is most likely going to be in pinch off at midpoint voltage. What comment can you make about the value of lambda? Is it going to be smaller than the short channel transistor or larger? It's going to be much smaller, right? Because if you remember that delta L by L, if your original L itself is very large, as it will be for a long channel transistor, the value of lambda is going to be negligible. So let's say that the value of the lambda is so negligible that it can be assumed to be 0. Then we saw the problem, right? If I assume lambda to be equal to 0, you will see this again if you write the whole expression and derive. You'll see that the gain is going to be proportional to lambda n plus mod lambda, which means corresponding to the midpoint voltage, your gain is infinity. It doesn't mean that the characteristic is an ideal VTC. It's just that you will have a curve like this, where here you have infinite slope. Okay. But for a case like this, if you were to do a linear piecewise approximation, you will end up with an ideal VTC, where VIH and VIL will be equal to the midpoint voltage. So thankfully, once you assume lambda equal to 0, the equations for deriving the exact VIH and VIL are not so complicated, right? So we can write out the equations and then see what region the transistors are and derive for VIL and VIH. So we can quickly do that because this is going to give us some interesting results. So let me start with calculation for VIL. Can you quickly tell me the region of operation? So when we are dealing with VIL, we are dealing with the point here. So this is VIL. I'm going to call this point as VO1, which is very close to VOH. What would be the region of operation of NMOS and PMOS? PMOS will be in linear region. NMOS will be in saturation. So the same old, we write the equations for the current and equate it. So NMOS is in saturation region, half mu n COX Wn by Ln into Vn minus Vtn the whole square. What is the equation for PMOS current? Mu P COX Wp by Lp into VDS, into VSD, where VSD will be equal to VDD minus V0 into VSG, which is VDD minus Vn minus mod VTP minus VDS by 2. So I take this portion this side. And as usual, we call this as R. Can you differentiate this? Differentiate this, substitute dV0 by dVin to be equal to -1, Vn equal to VIL, and V0 equal to VO1. And tell me what expression you get for VIL. Careful when you're differentiating this side. You have V0 here, and you have both Vin and V0 in this term. Once you make the substitutions and take the appropriate parameters to the LHS and RHS, you will get VIL is equal to VTN plus R into twice of VO1 minus VDD minus mod VT. This whole thing divided by 1 plus R. So you can do the calculation for VIH also in similar fashion. I'll give you the expression right away. So VIH you will get as VTN plus twice of VO2, where VO2 is corresponding to this voltage. We can substitute at the end and see how that equation is changing. For now, we'll derive with VO1 and VO2. This corresponds to VIH, right? So VO2 plus R into VDD minus mod VTP divided by 1 plus R. So let's take your suggestion and substitute VO1 to be equal to VDD and VO2 to be equal to 0. What do you get as VIH and VIL? What relationship? So we are interested in calculating what is VIH minus VIL, the width of this transition region. Okay. So if you substitute VO1 equal to VDD and VO2 equal to 0, you will get this as 0, right? Which means there was no point in doing this whole calculation, right? So we'll make a different approximation to get more insight. So all that I'm going to say is the characteristic symmetric. That is, if you had VO1 here and VO2 here, all that I'm saying is this width is same as this width, right? So VDD minus VO1 is equal to VO2. Can you substitute this and then tell me what is VIH minus VIL? It is? You should get this as equal to twice of VO2. So the core idea here is this. VO2, we said, is already very close to 0, right? Now, VIH minus VIL is simply giving you twice of a very small quantity. So the transition region for a long channel transistor is going to be very, very narrow. So if I were to plot the VTC for a long channel and a short channel transistor on the same curve, for a long channel transistor, you will see something like this. And a short channel transistor will have a larger slope. And this calculation allows us to bring this fact very nice. Is this clear? Then we can wrap up the class here today. Thank you.